Alright, let's continue on this road. This program I've been going through it a little bit, but it does like video learning and then practice problems, so it's a little bit different than the last one. I wasn't sure how it was going to work, but
we've just seen an example of an algorithm that computes floating point numbers as an answer. And we've been playing with floats earlier on. I now want to take a little sidetrack to talk about floats and how they're represented inside the computer. And in particular to deal with something that you may have experienced earlier on in the course, where you'll get answers that'll give you some funny number where you're expecting 3.0 and it gives you 3.000000125 or something else. To deal with this, we need to go inside the machine for a second and talk about how floats represent real numbers. They certainly approximate them, but it's useful to get a sense of how the machine actually stores it, because it can't store an infinite number of decimal points or digits after the decimal point inside the machine. Here's the basic idea. Let's start with a decimal number, the numbers you're used to dealing with. The number 302 is really 3 times 10 squared plus 0 times 10 to the first power plus 2 times 10 to the 0th power, or 1. It's 300 plus 0 tens plus 2 ones. Binary numbers, which is how the computer stores things, are actually represented the same way, but now in terms of powers of 2. So the number 10011 in binary is 1 times 2 to the 4th plus 0 times 2 cubed plus 0 times 2 squared plus 1 times 2 to the 1 plus 1 times 2 to the 0, okay, which is actually 16 plus 2 plus 1, or 19, in decimal notation. Internally, the computer represents every...
I need to see that much bigger. Let's rewind that. I'm like, wait a second. Okay, here we go. I broke it.
Really, 3 times 10 squared plus 0 times 10 to the first power plus 2 times 10 to the 0th power, or 1. It's 300 plus 0 tens plus 2 ones. Binary numbers, which is how the computer stores things, are actually represented the same way, but now in terms of powers of 2. So the number 10011 in binary is 1 times 2 to the 4th plus 0 times 2 cubed plus
1 times, I'm going to write it down. 2 to the 4th. This is good to know. This is another way to think about binary. Times 2 cubed plus 0 times 2 squared plus 1 times 2 first plus 1 times 2 to the 7th. So that's 16 plus 2 plus 1 is 19. So 1001 is 19 in binary.
plus 0 times 2 squared plus 1 times 2 to the 1 plus 1 times 2 to the 0, okay, which is actually 16 plus 2 plus 1, or 19, in decimal notation. Internally, the computer represents every number in binary, whether it's an integer or it's a float. How would we use that idea to think about how do we represent floating point numbers? Well, let's think about how we could convert a decimal integer into a binary representation, and then we'll do the fraction portion of it.
Converting decimal integer. This is binary. Go. I'm so glad Friday is here. So glad.
So given a decimal integer, how would we convert it to binary? Well, let's take an example. My example would be the one I just had before. 19 in decimal is 10011 in binary. If I had 19 or anything that represents that number, how could I get it out? Well, what I can do is the following little trick. I can take the remainder of that number relative to 2.
Okay. Okay, so modulo 2. Okay. Gives us the last binary bit, all right?
And that remainder actually gives me the last binary bit. It'll give me this bit right here, because that's the remainder that's left when I divide by 2.
Okay, that's good to know. Very good to know. lots of note-taking in this one, more than the last one even, but it's much more in-depth, so it's good. Okay, let's keep going. Oh, so this is like bit shifting. Oh, yikes. I'm feeling like these exercises today are going to be a little bit rougher than I'd like for Friday, but that's what we're doing. Oops.
If I then take x and divide it by 2, integer-wise, using that double slash idea, all of the bits get shifted right.
Ah, so we can make that into a loop. Okay, and then we divide x by 2. Okay, and then an example, 2 to the third plus 0 times 2 squared plus 0 times 2 to the first plus 1 times 2 to the 0. And we keep doing successive divisions. Remainder is the next bit and so on. Okay. Yep, so the remainder of this one would again be 1, and we would divide it by 2 with the double dividers to get to the next digit, which means 0. Right. Okay, if you say so.
That is, x double divide by 2 is now 1 times 2 to the third rather than 2 to the fourth, plus 0 times 2 squared rather than 2 to the third, plus 0 times 2 to the 1 rather than 2 squared, plus 1 times 2 to the 0 rather than 2 to the 1. Or another way of saying it is, notice I've taken these digits and just shifted them to the right. If I keep doing successive divisions like this, I can keep track of each of the bits that comes out, because the remainder gives me the next bit. And when I'm done with all of that, I've converted to binary form. So basic idea, given an integer, take the remainder with respect to 2, that's the low order bit, divide integer-wise by 2, shifts right, do the same thing until I've exhausted the entire integer representation. So here's a little piece of code that would do exactly that.
Gotta write this down.
If the number's less than 0,
for sure. I'm having to do this converting decimal integer into binary. Gotta make my notes pretty. Also helps me find things later, because if you're looking through, then you can have like, I have visual coloring cues, like, okay, this is a different topic. Yeah, let me tell you, the secondary stream I do at Much Me Work is not the easiest thing to start, for sure. There's a lot of hoops to jump through. All right, let's write this down. So just making it positive equals negative. Else, what do we do with it? First run the test, is it negative and false? Results. Votes. Number is equal to 0. So it's -0. And while number greater than 0, so it's 3. Modulo 2 plus, so it's that number equals number divisor 2. Alright, we got it. Okay. It's negative. So it's okay, now we'll watch the explanation.
I'm going to put on a flag that says it's negative, and I'm going to use the positive version of it by taking the absolute value of that number. Otherwise, I'm going to put in a flag that says it's not. And then I'm going to simply accumulate those results. If the number is equal to 0, it's just 0. That's pretty obvious. Otherwise, as long as the number is greater than 0, I'm going to do remainder, add that in, because that's the next bit into result, do the division to shift it to the right, and keep going. So if I look at that, here's a simple example of doing that conversion, converting decimal to binary. I'll start with a real simple example. If I start off with number as 3, and I do that computation, it didn't print anything, but the result is sitting in result. And there I get it. The binary representation of 3 is not surprisingly 1 plus 2. Let's just check to make sure I wasn't misleading you when I said 19 was in fact what I claimed it was. So if I make it 19, and I run it, and look at result, it gives me back 10011, exactly as I said. All right, cool. So I can take integers and convert them into binary. But I started talking about floats. So how do I deal with the fraction part of this? Well, I can do almost the same thing. Let's take an example. 3/8 is 0.375, and in binary, that is 3 times 10 to the minus 1.
Good luck. All right, here we go. Back to here again.
Plus 7 times 10 to the minus 2, plus 5 times 10 to the minus 3. It's just the digits associated with each of the placeholders. Here's the trick I'm going to put. If I can find a power of 2 big enough to convert all of that into a whole, I can do almost the same thing. Let's take an example. 3/8, if I make it 9.
Okay, there we go.
It gives me back 10011, exactly as I said. All right, cool. So I can take integers and convert them into binary. But I started talking about floats. So how do I deal with the fraction part of this? Well, I can do almost the same thing. Let's take an example. 3/8 is 0.375, and in binary, that is 3.
Okay. Fractions. I want to change colors. Times 10 to the minus 1. 7 times 10 to the minus 2 plus 5 times 10 to the minus 7. Okay.
times 10 to the minus 1, plus 7 times 10 to the minus 2, plus 5 times 10 to the minus 3. It's just the digits associated with each of the placeholders. Here's the trick I'm going to play. If I can find a power of 2 big enough to convert all of that into a whole number, that is, multiply it by something so that it gets converted into a whole number, then I can convert that into binary. I just did that. I know how to do that. And then when I'm done, just divide by that same power of 2, and I've got a representation in binary of the fractional part of this number.
Okay. So we have 0.375 times 2 to the third plus 3 decimal. Convert 3 to binary, which is 1, 1, and divide by 2 to the third. To get 0.011, which is binary. Crazy. Okay, let's watch this.
In this case, I picked an easy example. 0.375, if I multiply it by 2 to the third, or 8, that's going to give me out 3 in decimal. I can then use what I just did as my trick to convert that to binary. That's 1, 1. And then I divide by 2 to the third, which simply says shift it right 3 points. And there is the binary representation of that decimal fraction. That's cool, right? It's a really neat idea. What am I doing? I'm using something I did for one computation, but converting another problem into the same problem. In this case, given a fraction, I'm saying find a power 2 that shifts it into an integer, use the same machinery, and then shift it back. And I'm simply taking advantage of powers of 2 because that's simply moving the placeholder, if you like, for the decimal point, or I should say the binary point, in a binary representation. All right, there's code that'll do it. I'm not going to walk through it. I'm going to let you look at it. I'm simply going to show you that this will actually convert
Wow. What's the handouts for this one? Does it come in with it? Let's see. Yes, it does. So where are we going to put this? Extract all. Oh, I already have them all. Oh, maybe there was some new ones, I guess. Whatever, too bad. All right.
decimal to a binary fraction. So if I take this and I run it, in this case it says give me a decimal between 0 and 1. Let's pick out a nice example. Let's start with the one that we had, which was 0.375. Sorry, let me make sure I'm here. And it says, oh, I'm going to tell you when I've gotten through it to get it up to something that is big enough, how many times I have to shift it over, what's the remainder, and there's the printed solution. Let's be daring and try another example I haven't tried before, just to make sure that it actually works. So again, we're going to call this out. It says, give me a number between 0 and 1. And I don't know, let's take 0.333. And what do I get? Well, it goes through a whole lot more computation. It's telling me what the remainders are, but it's running through that computation, and it says the binary representation for 0.333 is this horrible looking mess you see on my computer screen down there. But the point of this is, now I can take any floating point number, convert it into something that can be represented inside of the machine in binary form, and use it. And that, by the way, is why you will occasionally see these strange things where you're expecting 3.0 back, and it has a little bit of an extra piece on it because in binary, it can get close to it, but not quite to the place it would like. But with that, we now have a way of understanding how we can represent floating point numbers inside a machine where everything is stored just in terms of binary bits. What are some of the implications of this? If there is no integer p, such that a power of 2 multiplied by x gives me a whole number, then the best I'm going to get is an internal representation that's close, which is why I won't get something exactly right. And obviously I'm only going to do this so many times before I run out of powers of P to use this. It also suggests that when you want to test a quality of floats, you should be careful. You really don't want to given two floats x and y, you really don't want to use double equal sign, because it's going to check to see, is the binary representation exactly the same? It might not be. It might be really close. So we're always better off using the absolute value of the difference of two floating point numbers. Is it smaller than some small number, rather than...
Okay, so don't compare float numbers. So much stuff. Don't compare float numbers directly. Instead, what do we use? We use the absolute value of the difference between x and y rather than x. Okay. Some small number. So like 0.001 or something like that.
than using the more exact, are they exactly the same? And then finally, as I've already said, we may not always get an exact representation for a for a float in the way we would like, but if I do print of something, why does it always return what I'd expect, even if the representation is indifferent? And the answer is because wonderfully the designers of Python designed it so that it would automatically round to the closest representation in terms of that floating point number. There are floats. Now we got ability to do integers and floats. We're in good shape.
Okay, now we answer some questions now that we got through that video. Like 10-minute video took me like 20 minutes. Oh my god. That's 3, so that's not it. 0, 1, 2, 3. So this would be 2 to the third. 2 and 1. I don't have a lot more notes on this back here. 1 is 7, so 1, 1, 1. Let's see. Add 1 to the end there, so it would be 1, 1, 0, 1 is 8. 1, 1, 1, 0 is 9. 1, 1, 1, 1 is 10, and 1, no, that should be 1, 1, 1, 0. 1, 1, 1, 1 is 9. 1, 1, 1, 0. Is that right? No, I don't think that's right. Dang, I don't remember how to do this. I still haven't wrapped my head around binary, obviously. And the way he described it was better. 1, 2, 3, 4 is 15. All right, let me just look at this magic. Look at this magic. I can say, what is the number 11 in binary? It is 1011. So that means 1010 is 10.
Remember, you're a grown-ass woman. You can use calculators when the fuck you want.
That's right, I do what I want. It's a calculator. Right, true or false? General representation of the decimal number 1 divided by 10 requires an infinite number of digits. Oh, it doesn't let me do decimals in here in programmer mode. No! All right. Now, let's try converting the decimal integer to binary. Fractions in binary. So 3 times some decimal. Okay. Exercise. Let's do a different color. Zero 0.1, so 1 divided by 10, which is the same as times 10 to the minus 1. So then we take 0 0.1 and multiply it by something that would make that a whole number, right? Because we want 8 times 0.375, so we get a whole number. Okay, 3. Oh, because it's 3 here, maybe? Ugh, math hurts my brain. Let's try 2 to the 5th. What do we get? 32 times 0.1. To the what? 4th? 16. That should work. times 2 to the 4th equals 1 decimal, 1.6. Do I have to get it to a decimal? I don't think gotta be at least good with this. This has got to work. So then we convert 1.6 to binary, which would be the same as 1 times 1 in binary is 1. Point and 6 is 110. Is that how that even works? Oh, okay, so apparently it is true. Yes, okay, so I was right. Oh, it does have to be a perfect integer with no remainder. Okay. Which is why it would work, because 2 to the power of anything doesn't give us something that ends in a 0. Let's see how we did. Which one didn't I get right? Okay. I guess it's false. It's not always an approximation. Only when it's a float, I guess it's an approximation. Okay, next we're gonna go watch another video. Look, it looks like it might be something surprising for us to learn this time.
Now that we've got an understanding of floating point numbers, now that we've got the idea of generalizing guess and check methods
Is it
to
just
do
me,
things
or
that
is
do
this really,
approximations
like,
to find
fuzzy?
solutions to things, we can really start building some pretty powerful programs. We've already seen something that searches for cube roots of numbers even if they're not a perfect cube, square roots of numbers even if they're not a perfect square, and we've seen how we can get to quick solutions very nicely using things like bisection search, have great accuracy and still find good answers. I want to show you one last example, just to give you a sense of the power of computation we can now do. I'm going to stick with the idea of finding roots of things, but show you how you can actually capture things very dramatically. And that's to use a technique called Newton-Raphson. It was discovered by Sir Isaac Newton 3 or 4 centuries ago, also discovered by Raphson at about the same time. And here's the basic idea behind Newton-Raphson. It's a general approximation algorithm that's going to let us find roots of any polynomial in one variable.
Okay. such that P of R is equal to 0. Okay, so another example, Px of x squared minus 24 to find the root of 24. Okay? And then, let's see, if g is an approximation of the root, then g minus p of g divided by p derivative of g. Okay.
And one variable. So that could be, for example, a polynomial like this. I've got p of x is some coefficient times x to the n plus some other coefficient times x to the n plus minus 1 and so on. And what I want to do is find the value r such that p of r is equal to 0. It's called a root. It basically is the root of this equation. Newton-Raphson will apply to any polynomial. I'm going to show you an example of using it to find square roots. And you can say, well, I already did that with bisection search. You're right. But it's a nice way of looking at how we can generalize the computation. So in particular, if I want to find the square root of 24, I'm going to use the polynomial x squared equals 24. Because if I can find the value of x for which this is 0, then x is, in fact, the square root of 24. What Newton showed was that if g is a good guess to that root, then you can get an even better guess by taking g and subtracting from it the polynomial evaluated at g divided by the derivative of the polynomial evaluated at g. And if you haven't done calculus and you don't know what a derivative is, don't worry. We're going to show you what it is in this simple case of a square root. But I want to let you see the power of doing Newton-Raphson. So Newton showed if I got a good guess, I can make it better by taking p of g divided by the derivative of p at g and subtracting that off of g. So in the simple case, if I've got an equation that is some constant times x squared plus another constant, then the first derivative of c times x squared is just 2cx. So in my case of looking for square roots, x squared is plus k is the thing I'm trying to find a solution of, the derivative is just 2x. And so Newton-Raphson says, given a guess for the root, take the polynomial at that point, which is g squared minus k, take the derivative of that point, which is just 2g, take that ratio and subtract it off from g. Cool. We ought to be able to build that, and we can. It's a nice, tight, little iterative loop. So here's a nice way of generating the guesses. again, I'm going to have some epsilon that's going to let me decide how close I am to an answer. I got the thing I'm going to look for, and my initial guess I'm just going to pick as that value divided by 2. And then here's the loop. As long as guess squared minus y, the absolute value of that is too big, I'm going to keep going. And as before, I'm going to count the number of guesses to see how long it takes. Each time around, I'm going to use that little equation from Newton-Raphson. I'm going to take g squared minus y, divide it by 2 times g, or guess, subtract that off of guess, and go back around. That's just the thing I did before. And I'm going to run through that loop until I get something close enough, and then I'm going to jump out. So let's see what happens if we do it. I've got the code over here. I'm going to load it in and run it. And in 4 guesses, we've got a good solution. 4. Okay, it's a whole lot better than 30,000, which is where we started. With the bisection search, it was about 15 or 20. Now I've got it down to 4. Let's pick another example. Let's take my favorite example here of 54. Same thing, and I run it. And in 5 guesses, it gives me a good solution. This is really cool. I know you don't believe it, but it really is cool because it lets me not only find cube roots and square roots, it lets me find the solution to any equation very quickly. So what we've now seen is that this idea of a guess and check method builds on reusing the same code over and over again. It takes the idea of a looping mechanism and adds to it, building into it different ways to generate the guesses and then checking to see whether I'm close enough or I want to keep going. And we've already seen now simple exhaustive enumeration, bisection search, which cuts down the amount of expense dramatically, and now, at least for root finding, Newton-Raphson, which improves it even more formally. So you've already seen 3 different classes of algorithms, and you've got a lot of tools for doing numerical computation. We're going to come back to that as we move on through the course. Let's think about what we've been doing so far. We started introducing elements to our language. We started off with simple things, basic objects, ways to do arithmetic operations on them, ways to compare them. We introduced conditionals as a consequence of that. And we started looking at the first version of ways to actually put things together into pieces of code. So we've covered language mechanisms. We've also covered the first notion of for and while loops and therefore of iteration. And we've also seen that we could write different kinds of computations, each one in a different file that I save away on my machine so I can use when I want to do something with it. Each file contains a piece of code, and each piece of code is some sequence of operations. It could be a simple branching program, it could be an iteration like a for loop or a while loop, it could be something else. This is fine when our code consists of a few lines. This is fine when our problems are very small. But it doesn't really scale very nicely. As I start thinking about pieces of code that might be hundreds or thousands of lines long, simply doing it this way is a real challenge. It's hard to keep track of the details. It's hard to make sure that I've got the right information in the right place in that code. Does this go at line 95 or at line 296? I need a way to really capture this better. I need a way of structuring my code, structuring my computation so that I can think about it much more efficiently. And that's what we're going to introduce now. One of the things to keep in mind is, in fact, good programming is more than just adding more code. In fact, I would argue that a good programmer is measured not by the number of lines of code she's written, but by the amount of functionality that she's provided, the ability to do computations easily. And so to make that happen, we're going to take a really nice pivot, introduce a major new thing, and that's the idea of a function. We're going to describe it in a second, but the idea of a function is it's going to give me a way to encapsulate pieces of computation. And in fact, a function is intended to give me 2 really important aspects of computational thinking. Decomposition, sometimes also called modularity, and abstraction. So what do those mean? Let me give you an analogy, something a little bit different.
So function allows for decomposition or modularity and abstraction.
I'm sure you've all seen a projector. I think of a projector as a black box. Now, the one I'm showing here happens to have a black box around it, but by black box, I literally mean a construct whose details I don't understand. In fact, most of us don't know what's inside it, how it actually works. If you open it up, you see a bunch of electronics, and unless you're a really good electrical engineer, you probably don't understand how it works. It doesn't matter, because you know the interface. You know the input-output behavior.
That being said, we also have some libraries installed, and those are not coming up for us today. I'm not sure why, but they're not. And that's going to be a problem later.
Okay, here we go. Sorry, just to double check those out.
And in fact, that black box comes with a standard interface that says if I plug an appropriate piece of electronics into it, that box can communicate with it, and it's going to produce an output. It's going to show slides on the wall. That's the notion of abstraction. It's the idea that once I've built something, in this case a projector, might be a piece of code, once I've built something, I don't need to know what's inside it as long as I know how it works. So abstraction in some sense comes with a contract that says, if you give me appropriate inputs, I'm going to behave in an appropriate way. That's a really nice idea. That's something that we're going to want to use, and we're going to use it with code. There's a second piece to it, and we'll stick with the projector idea. If you happen to see the opening ceremonies for the Vancouver Olympics, there was a wonderful display in which there was a huge multi-story high structure in the middle of the rink onto which images were projected. Now, it wasn't one projector, it was way too big. It was a sequence of projectors. Each of them took an input, each of them produced an output. And they all worked together in synchrony to produce that wonderful larger image. That's the second big idea, decomposition. That I can, in this case, take different devices, have them synchronize so that they work together to achieve an end goal. I want to use the same thing with code. So we're going to apply those ideas to programming.
Okay. Decomposition. Breaking problem. Into different self-contained pieces. That's how I was originally designing it. Abstraction. Suppress details in method to compute something from that computation. It's probably talking about lambdas.
Decomposition. I'm going to break a problem up into different self-contained pieces. And once I built them, or even better, once somebody else has built one of them for me, all I need to know is what does it expect as input and what will the behavior be when it gives me an output. And the second big idea, abstraction. That I want to be able to suppress the details inside that method in order to be able to compute something using that computation. And in fact, I just said them the wrong way. What I first described was really abstraction. Decomposition is that idea of breaking it up into smaller pieces. With those two things together, we're going to now look at how do we make programs have those two properties. Okay, inside of code, with decomposition, we're going to do the same thing we did when we talked about having multiple projectors working together. When I'm going to structure a big piece of code, I'm going to divide it up into modules. And those have the property that they're self-contained. That means they have everything they need inside of them. I'm going to use it to break the code up into pieces that I can separate apart. And they're intended to be reusable. I can use them multiple places. If you think about it, so far, even if I have a little file, I can only use it once. or if I want to reuse it, I've got to go back and recall the file. Here I'm going to structure code so that I can use it in multiple places. And we're going to see that this idea of dividing code into modules is both going to keep the code organized and coherent. It's going to be easier to structure. Today we're going to do decomposition with functions. And in a few weeks' time, we're going to see how to do decomposition with classes. An equally powerful idea. We're going to suppress details with abstraction. Again, I said with the projector, I don't need to know what's inside, I just need to know what it does. In programming, we're also going to think of a piece of code as a black box. I don't need to see the details inside once I've written it, or especially if somebody else has written it for me. I, in fact, don't want to see the details inside. What I simply want to know is that it's going to work the way it was advertised. And we're going to achieve abstraction with something called a function specification or a doc string. And in a second, we're going to see examples of both of those.
Okay, so we achieve abstraction achieved through function specifications. Or strings.
But there's the idea. Abstraction, decomposition. Two powerful ideas that we want to capture inside a computation. One of the things that comes out of this is not only do they work well together, but they can then be used many times. And in fact, not only can they be used many times, I only have to debug it once. It's one piece of code. If I want to make a change to it, I change that piece of code. Anything else that depends on that code will inherit that behavior because they simply depend on that code.
Okay. Next.
So how do we create this notion of abstraction and decomposition in Python, or actually in any programming language? And the answer is we introduce the idea of a reusable piece of code or a chunk of code called a function. Functions are not going to be run in a program until we actually ask them to do that. So as opposed to things I was typing into my shell, every time I typed in an expression, it was invoked or evaluated, I'm going to create a definition of a function. And when I read that in, it's simply going to create the ability to do that computation, but not actually call it. And we'll see an example of that in a second. What are the characteristics of a function? Several. First, it has a name. That makes sense. I've got to be able to refer to it in the same way that I had a variable as a name for a value. A function will have a name. It will also take a set of parameters. These are arguments or values that I'm going to use inside the function when I do a computation. It's going to make sense in a second when we look at an example. Every function has to have parameters, but the number of parameters could be 0. Or it's a funny way of saying it's going to take in a parameter list, but in fact, it may need no parameters, and I'm going to decide when I create a function how many parameters I need. We'd like every function to have a doc string. That is a documentation that tells me what the function does. We'll see an example of that in a second. And finally, a function has a body. And the body is the sequence of commands or instructions that we want to actually have happen when we use the function. Those are a lot of words. Let's look at an example to get a sense of this. Here's a definition of a function, and I'm going to walk through each of these pieces. So, first part of it is, I've got a keyword, in this case def. And it is a keyword, meaning it's a special symbol to Python that tells me I'm about to define something. In this case, I'm about to define a function. That is followed by a string that is the name of the function. In this case, it's is even, or is underscore even. That's the name of the function I'm going to give, and the name I'm going to give to this function. That is followed in parentheses, in those parens, by 0, 1, or more parameters. In this case, I've got 1. And I'm giving it a name. Think of it like a variable name. I'm saying I'm going to use the name I as the name for a parameter inside this function. And that's then followed by a colon to tell me I'm done with the top line of the definition. I'm about to follow it with other information. So keyword def, a name, and in parens, some number of parameters. Immediately below that, in triple double quotes, which is a wonderful expression, is a doc string. It's up to you how to use this, but traditionally you would specify what's the input to this function and what's the output of this function. It's a little bit like a contract. In this case, I'm saying I'm expecting one input, I'm calling it I, and it's a positive integer. And what I'm going to return is true if I is even, otherwise I'm going to return false. As we'll see in a little bit, one of the nice things about a doc string is, once I've defined this function, if I go to call it, which I'm going to get to in a second, Python will automatically bring up a little window that tells me the doc string, that reminds me what the conditions for this function are, which is great. So, keyword, name, parameters, I've got a doc string. Immediately below that is the body of the function. This is the sequence of commands or expressions I want to evaluate when I'm ready to use this. Notice the indentation. All of this is indented here. This is telling me where the body of the function is. And in fact, it will be everything until I get back to something that returns to the left-hand side of the editor or of the shell. In this case, I've got two expressions in my body. It's going to print out simply the string hi, and then it's going to return a value. I'll come back to the return in a second. There's how I write a function. Now, how do I use it? The function has a name. The same way I could use a variable as a name inside of an expression, I can use the function name. And in particular, later on in the code, I can say an expression like is underscore even, and then an open paren, followed by an expression whose value I'm going to use inside of that procedure, followed in this case by a closed paren because there's only one parameter. I call this invoking or calling the function. I'm using the function. We're going to look at some examples in a second, but the basic idea here is that when I call this function, I'm going to take the value 3 in this case, and everywhere I see an I in the body of the function, I'm going to use that value in place of I. And in fact, if I look at it then, inside of this particular expression, I'm going to print out simply the string high. And then I'm going to evaluate this particular expression. And it has the keyword return followed by an actual value. Now, I just said, in this case, if I've called isEven with the parameter 3, I now holds the value 3. So I'm going to evaluate 3 remainder 2 and say, is that equal to 0? In this case, it's not because the remainder is 1. And I'm going to then return that value to whoever called this function. So that's the expression I want to evaluate and actually return. So it returns a keyword that tells me I'm ready to stop the computation, and whatever the following expression is, that is the value I'm going to give back to the person who asked for it. In this case, it was simply at my shelf. But we'll see in a second, it could be somebody else that's going to use it as part of another computation.
Okay. I'll do some activities. 12 minutes. Oh god, this might just take me the rest of the day.
You can do it.
I can do it!
You
I
can
can
do
do it! Alright. That's a Python Boolean is true and false if we operate in terms of where the integers 1 and 0, but it's ugly. So pretend that it isn't true. Okay. Yep, computer integer or upload. Select no. Okay. This will only be a float. Right? Because if either one is a float, it will return a float. Hold on. I wrote all these down. Here they are. So sum, if both are integers, result is an integer. If one or both are floats, the result is a float. So it's a float. What about greater than? Can be an integer, a float. No, I guess. Indicate the type of output that the function E will yield. So then anyone can be integer or float. That was it? I'm wrong on like all of them. No, only half of them. Okay, that's good. X can be an integer or float, Y can be an integer or float. Return X greater than Y, and it's not. Does that mean it's just an integer? Float? this be a Boolean it returns, like true or false? I don't think so. Try float and flow. Nope, it's not float. Let's try Boolean here. Yeah! Yeah, so if it has greater than, less than, or equal to, it automatically has to be a Boolean. And then this one is going to give us what? It's not number, it's not float. What's the answer to this one? None type. Why is that? Ah, it doesn't have a return statement. Since it doesn't return anything, Python by default returns the value whose type is none type. Okay. Next. Well, that wasn't as bad as I thought it was. I see that now, but when we get over here. Okay. Turn. Oops, that was terrible. What are we returning here? Return what? Return X. Star star square. Submit. Yeah! I got that one right. Woo! Hooray! Right, Python function, evaluate quadratic a, b, c, x that returns the values of the quadratic a times x squared plus b times x plus c. This function takes in 4 numbers and returns a single number. Those are closed, that's closed. There we go. And there's 1, 2, 3, 4. And then we take it from there and plugged into there, submit it. No! Do we need more parentheses? That's all. No? Return is outside the function? Okay, 1, 2, 3, 4. Yes, so it was right the whole time. I was missing one space. No, I would have gotten that one the first time too. Damn it. Oh, here's another video. Okay, before we start this one, I'm going to take a quick break. I will be right back. almost back, almost. Oh, very tiny. Hold on, just a little. Alright, let's get back to it. Let's get back to it. Ugh, my hair's drying. The process of burning. Takes forever to dry. Let's get on with this.
This idea of function invocation, function calling, is really important. It's central to how we're going to use functions to control our code. So I want to work through in a little more careful detail exactly what happens when we call a function and how we get values associated with variables. You'll see on the screen here I've got a little piece of code. I'm defining a function called f, I'm binding x to 3, and then I'm going to call f with the value of x and bind that to z. Let me show you what happens if I actually run this. So on my computer, I've got a version of that file, and I'm going to load it into my shell. And what it prints out, as you can see, is it says in f of x, x is equal to 4. How'd that happen? What's going on here? Because x seems like it's used in a lot of places. So this is going to be an important opportunity to look at how functions are called. As I've already said, the key idea is each formal parameter, in this case I only have one, is going to get bound to the value of the actual parameter when the function is called. And then when I call a function, I'm going to create a new environment, sometimes called a frame or a scope, a new place in which I'm going to bind variables and relative to which I'm going to evaluate the body of the function.
Okay, so I'm going to write this down, but I understand what it's saying here is like you might expect this to be 3, like to return 3, but it's going to return 4 because it goes through the whole function thing and makes that. Okay. Variable scope. Scope is mapping of stops.
Think of that scope as a mapping of names to objects. And in fact, we've been using that idea. When we were just talking to the shell, when we defined x to have a value, say, of 5, we were creating in the global scope or frame a binding of the name x to the value 5. Now, let's look at this in a little more careful detail. Imagine I now do what I just did on my computer. I evaluate this sequence of expressions. There's that formal parameter. There's the actual parameter I'm going to use. And let's look at what happens. I evaluate that, and in that global frame, I create a set of bindings. First one is, evaluating that definition binds the variable name f to something. Oh, but that's important, because that something is just a set of code. I haven't run f yet. I haven't tried to do x equals x plus 1 or anything else. I've literally, in the machine, said, associate the name f with a chunk of stuff. Next thing I did was I evaluated x equals 3, and that just creates a binding. We've seen this before. So in the global scope, x has a binding to the value of 3. And now I'm ready to evaluate that last expression, which says give the name z the value of calling f on x. And I'm ready to do that. Now remember, before I can actually do the binding of c, I have to get the value of that expression. So calling f literally creates a new scope, a new frame. It will actually inherit things from the global frame if it needs it, but right now I've got a new environment. The definition of X has a formal variable X.
Okay, I think I need to rewind this and write this down a little bit to understand better, because I think if I don't understand this, I might sometimes get results that are not what's expected or what we want. So let me just write this down. Example. This is why it takes me so long to write down a lot of stuff. But my notes do help me. I use them for the binary. My binary notes on the Codecademy, that helped a bit. So they work. Notes, man. Notes are life. This is the formal parameter, right? Let's back up just a little bit.
Because that something is just a set of code. I haven't run F yet. I haven't tried to do X equals X plus 1 or anything else. I've value 5. Now, let's look at this in a little more careful detail.
Okay, here we go.
Imagine I now do what I just did on my computer. I evaluate this sequence of expressions. There's that formal parameter. There's the actual parameter I'm going to use, and let's look at what happens. I evaluate that, and in that global frame, I create a set of bindings. First one is, evaluating that definition binds the variable name f to something. Oh, but that's important, because that something is just a set of code. I haven't run f yet. I haven't tried to do x equals x plus 1 or anything else. I've literally, in the machine, said, associate the name f with a chunk of stuff. Next thing I did was I evaluated x equal 3, and that just creates a binding. We've seen this before, so in the global scope, x has a binding to the value of 3. And now I'm ready to evaluate that last expression, which says give the name z the value of calling f on x. And I'm ready to do that. Now remember, before I can actually do the binding of c, I have to get the value of that expression. So calling f literally creates a new scope, a new frame. It will actually inherit things from the global frame if it needs it, but right now I've got a new environment. The definition of x has a formal variable x, and that's exactly what that corresponds to. And the value associated with it is the value of x that I passed in, which actually came from there. I know it looks a little confusing. I'm deliberately using two different values of x so you can see where the bindings come from. So f evaluated on x says, what is the value of x? I get it from the binding that I just previously. So inside that f scope, x is bound to 3. Now, relative to that scope, I'm going to evaluate the body of f. I want to do the work that f says it's going to do. So let me see what happens there. First expression says, evaluate x plus 1, and I'm actually going to go back for a second. Remember, in the f scope, x has the binding of 3. I add 3 plus 1, that's 4, and I create a new binding for x, but in the f scope, because that's where I'm doing the work. So it changes it here. It does not change the thing that was out in the global frame. That's great. Now, relative to that, I'm going to print out something, and on my computer screen, you saw it said, in f of x, x is equal to, the value of x in the f scope, and that's why I printed out 4. And then what it's going to do is it's going to return x. So literally, it's going to get the value of x in the f scope, which is 4, and it's going to return it to the person who asked for it. And what was that person? That was down here. We're doing the binding of z. So I've just returned to that binding a value for f of x, which is 4, and that creates the binding for z. If this is a little confusing, watch the same segment again, because this is an important idea. Anytime I do an rephrase that. Anytime I do an invocation of a function, I create a new frame. I bind the formal parameter of that function, or parameters if there's more than one, to the values of the expressions passed in, and relative to that frame, I now evaluate the body of that expression. When I'm done with the body of the function, if there's a return, I'm going to send the value back to whoever called for it, and erase or remove that frame because I no longer need it. Okay, with that idea, let's look at a couple of other examples. First, what happens if there's no return statement? Here's my function from before, is equal. But rather than returning is the remainder of I divided by 2 equal to 0, I just have the expression. So there's no return here. What happens in this case is that Python returns the value none, because I did not give a return. So Python will say, in a function call, if you don't have an explicit return, I return the none value. It represents the absence of a value. And unfortunately, that would mean in this case, I would not get back the answer of true or false. I would simply print out nothing, because there's nothing to be returned. Point of this is, anytime I want a function to do something, unless it's simply doing something we call a side effect, I always want to have at least one return that's going to give a value back. So remember to keep your returns in. In fact, that gives me a chance to talk about the difference between return and print. You can see the description here, and let's just do it quickly. Return only has a meaning inside a function. It's the only place we can use it.
Okay, I'm gonna have to write these down too, I'm sure. Okay. I thought we return. Okay. Let's change colors again. Hot pink. Versus prints. Meaning only inside a function. Only one return executed inside a function. Inside a function. Code inside function, but after return statement, not executed. What does that mean? After return statement, not executed. Okay, so code in a function after a return statement not executed. Is that what's saying? Code inside function after return statement not executed. As a value associated with it given to function call. Okay, and print can be used outside function. Okay. And execute many statements. Inside a function. Code inside function can be executed after print statements. And has a value associated with it outputted to the console. Okay, let's continue.
Inside a function. I could have more than one return. If I have branches or other conditionals, I might have different places from which I want to return. But only one return will ever be executed inside the function, because it's going to throw me outside of the function and return a value. Any code inside the function, but after the return statement, will never be executed. And of course, a return does have a value associated with it. It's given back to the person who called the function. By comparison, while return has a meaning only inside a function, a print can certainly be used inside a function, but it can also be used outside of a function. We've already seen that. We can also execute many print statements inside a function, and any code inside the function after that print statement can, in fact, be executed. Again, a print has a value associated with it, but it is simply output directly onto the console rather than being returned. So prints are going to be handy to have us pass information back to the user to let them know the status of a computation. Return is the way in which I'm going to get a value back to somebody who asked for it, whether it's me as the user or some other function call. With that in mind, let's look at, in fact, how you might have other function calls. So, not only can parameters have numerical values, they could also have other values, including being a function. So I have three definitions of functions here. The first one, A, takes no parameters. I said this earlier, but I'm going to say it again. Notice it has an open and closed param. That's important. I have to tell it that there are no parameters there. Function B takes one parameter, in this case called y, and function C also takes one parameter. In this case, it's z. What's interesting about this is how these functions are going to use them. And in a second, I'm going to run it. But notice, I'm going to call function A with no parameters, so an open closed paren to tell me there are no parameters. I'm going to call function B. It's going to take in one parameter. In this case, I'm going to give it a number. And function C is going to take in one parameter, but in this case, it's another function. Whoa, that's funky. It's actually okay. I can pass in the name of the function, and that will literally pass the actual function in to that parameter called for function C. Let's see what happens if we try this. So I've got that code loaded up over here. I'm going to pass it into my computer. And notice what it printed out. The first thing is it printed out inside function A. That came from calling this function, and that's the print statement right there. There is no return in function A. And so in fact, the print takes the value returned by function A, which was none, and it printed it out on my computer. I then take the next call. I pass in to the function B. Function B prints inside function B, right there, which is the next thing it did. And then it returns the value passed in, which is the value of y, which is 2. That gets added to 5, which is why on my machine I printed out 7. The print statement printed out 7. And then the last one, again, a little funky. I passed in function A as an argument for z in function C. And what happened? It printed out inside function C, and then it called a return of calling z with no arguments. And what's z? It's function A. Oh, that's nice, because function A then said print out inside function A, which it did. Return nothing, because there is no return statement. And so this print at the bottom then printed out none. We could step through it more carefully, but you hopefully get the idea. In each case, I'm simply evaluating the body with respect to a frame. And the arguments could in fact be other functions that I can invoke inside of a function call, which I did inside of function C. So, as a consequence, inside of a function, we can both access a variable defined outside as well as a variable defined inside. On the other hand, inside of a function, we can't modify a variable that's defined outside of the scope of that function.
Okay. Police probably. Let's see. So inside a function. Access variables.
And here I have three little examples just to give you a sense of that. What I'm going to do is show you basically what would happen for each one of these function calls. So I've defined f of x to be set x equal to 1, add 1 to x, and then print out the value of x. I've defined g to simply say print x, and then print x plus 1. And I've defined h to have a body that says simply increment x by 1. And I want to think about what do those things actually do. But let's look at the first each of those examples. In each case, I'm going to define x to have the value of 5. I'm going to call the function with that value of x, and then I'm going to print out x. What happens? In the case of f of x as 5 is passed in. I redefine x to be 1 inside of there. And then I add 1 to that value of x, which is 2. And then I print out x. So in fact, f of x is going to print out the value 2. And then this print statement is going to print out the value 5. Why? Because it sees the value of x defined in the global scope, which is where I am. What happens with the case of g? G says, well, first of all, I call g with the value of x, which is 5, which means 5 is going to be used in place of y. And then I say print x. You say, wait a minute, there is no x as a parameter to g. That's fine, because it then says if I can't find it in the frame associated with g, let me look outside. And there is a value, which is 5. So in this case, it's going to print 5. Then it's going to print 6, which is x plus 1. It has no return, so it's not going to do anything else. And then I'm going to print the value of x, which I get from here, the global environment, and it's going to print 5. Finally, I define h of y. I've done that. I've defined x to be 5. And now I call h with the value of y being 5. And what do? I'm going to print out, sorry, not that, rephrase that. I'm going to try and define x to be x plus 1. And let's think about what happens. So just to go back to this, I've already defined x from outside g. That's why I pick up that scope. What happens in the case of h? oh, I got an unbound variable error because I'm trying to look up the local variable value of x. I'm referencing it before I've assigned it. So in fact, I'm going to complain about this, and I'm not going to succeed. So we can see I can look up values outside the scope, but I can't change the values of those things outside of the scope appropriately. And that's a place where I have to be careful about how I actually use these different procedures. 3 different examples shows you different ways in which we can deduce how we actually pick up the values of the variables. And in each case, as I said, the x comes from the global or main program scope when I print out this value at the bottom down here. Okay. I'm going to show you one more example of scoping. I want to do a quick aside which says when you get to really tricky things, there's a nice place to go look, which is this place on the web called the Python Tutor that helps you sort these pieces out. And the last example before we move on to other topics is...
Let me write that down.
As I said,
No, I just missed it.
Global.
Oh no, I broke it again.
Global. Look.
Oh no.
Look.
No.
Look.
Make it smaller. There we go. Alright, we'll get there again. First, let's find pythontutor.com. Did I spell it wrong? I probably did. Yeah, I did. Okay, let's bookmark this page. Alright, let's do this again. We're going to start like here. No, we already did this one. No! Next. We need to go here. There we go. We don't have to go through all of them. I can just click up here. Oh, and it left us off the same place. Nice.
As I said, the x comes from the global or main program scope when I print out this value. That sounds neat. Here I've got a definition for g, and inside of there I've got a definition for h. And if I look at this code, I'm going to actually run it over here. Let's see what happens when I run it, and let's see why it does that appropriate thing. And when I ran it, it prints out the statement inside g of x, x is bound to 4. I want to see how that comes about. So here we go. When I evaluate, or when I just in fact evaluated inside my machine this description, here's what happened. As I saw before, in the global environment, g was bound to a bunch of code. Where's h? Hasn't happened yet. It's simply sitting in a chunk of code. We have not yet evaluated that body, so nothing has happened yet. X is bound to 3. So when I get to the point shown by the arrow here, this point in the code, I've got g as some code, and I've got x bound to the value 3. Now I'm ready to do a binding for z to be a call to g. We saw what happened before. G creates a new scope, and inside of that scope, I'm going to bind the value of x, and that x is coming from the formal parameter for g. The value is coming from the binding for x in the global scope, so x is bound to 3. And then I'm going to evaluate the body of g. And this is cool, because that says inside of here, I'm evaluating the definition of h. This is sometimes called an internal or helper function because it belongs only to g. The binding for h right here is to some set of code. Only when I'm inside of g can I use h. It's protected. That's great. Haven't used it yet. I just got a binding for h. And then what do? I create a binding for x, and notice what happened. I say get the current value of x, which was 3, add 1 to it, and then change the binding for x in the scope of g, because that's where I'm doing the work. So let's change that binding for x, but not this one over here, which is still 3. And then I do the print statement, which is why it says in g of x, x has got the value 4, because in fact I see this value of x over here. All right, almost done. Now I'm going to call h. Oh, h is a function. It's right there. And since I'm invoking it, I create a new scope. And this scope inherits from g, which inherited from the global scope. Inside of h, I bind any formal parameters. There aren't any. What do? I evaluate the body of h. So I bind x to the string abc. And then, what do I return? Oh yeah, nothing, because I have no return statement. So having done that binding for x, I'm done with the call to h, and there is nothing to return. Having done that, I'm now ready to do the last part of g, which was to return x. And you notice that binding inside of h of x equal to abc is gone. It's been garbage collected. And so I now simply return the value of x, which I know is defined inside the scope of g, and that gets returned as the value that I associate with z. Perfect. I'm now set because z has the binding 4. So there's a more complicated example, but you notice how those rules for scopes very nicely tell me, and more importantly, tell Python exactly how to look up values and how to use those to store new values as I do bindings.
All right. Time for more problems. Next. Okay. We have the following function definitions. Always my music over. See. No, good. It's still going. Okay. Just not quite. Oh, hey. Hi, how are you doing? Python is good. So I finished the Codecademy course and I tried working on my project again, and I was able to like piece what the project would be, kind of thinking about it as different functions or different tests we would need to do within the process. But then I realized I still didn't have the language to write those. So we did get a little bit further, but then I had to step back and basically I would say this is like a little bit intermediary Python, whereas Codecademy was, beginners. Also, how are you doing? I haven't seen you in a while. How was Finland? It's very early in the morning there, I guess. So he never has to go to a classroom, right? Well, I do have Python books, but I find for this kind of stuff, doing it is helpful. So already working in a space where you can do it is helpful. I should probably launch my spider here. I hope it comes out. I was gone for a bit. I'm feeling better now. Which part of me is like, it's kind of crazy to even feel okay with shit that's happening, but also like I have to be able to function as a person while everything falls down around me. Yeah. Especially hard when stuff out of your control. This is taking a long time to launch. I wonder if it's going to do it or not. I don't know. Okay, let's see what the exercise is. So these are our following functions. And then below is a session of Python shell. Provide the type and value of the expressions being evaluated. If evaluating an expression will cause an error, select type and write single quote error, single quote. The value of an expression is a function, select function, as the type and write function. Okay. What are we doing here? Yeah. And I also find like sometimes I'm just too anxious to do it. I'm just like I can't even deal with any of that. And I get too anxious that I don't see anybody, I don't talk to anybody, I don't want anybody to see or talk to me. It's like I'm in my little cave bubble of anxiousness. Leave me alone. What kind of beers did you have? Friends? Real life friends? So lucky. Although I'm going to be going up to Boston this month because today is June, first day of June. I'll go to Boston this month. It's going to be so much fun. I've never been before. Take the train with my friend. That was the whole point. I'm going with a friend, like real life friend. My one real life friend. Yeah. I feel like sometimes sometimes I need the pressure of doing it. Sometimes it can just be too much. And it's been a while since I streamed. Like, I think the last time I streamed was the 22nd of May, so it's been 8, 9, like 10 days. Yeah. 10 days of falling down. Got back up. Riding this horse called life. Provide the type and value of the expression. Okay, I read all that. A is 6. What are we doing when A is 6? What is that? Return X plus 1. Oh no, my battery's dying. Thank you. What's Boston famous for? Tea parties! Tea parties! That's where the revolution started. Reducing Twitch altogether. Yeah, I go through that too, where I'm just like, I don't want to see anybody. I don't want to talk to any person that knows me, because they're going to expect me to like be happy or be myself or be like how I normally am when I'm not so anxious that I can barely function with the like requirements of just being a person and a mother. So yeah. Yeah. It happens. All right. What are we doing here? It should return 7. It should return an integer 7. Because we put in an integer, get an integer out. Okay. A is negative 5.3. It can be an integer or a float, so we should get negative 4.3. Should be returned. And it'll return a float. Oh, they're getting tricky now. We know that A of 6 is 7, and we do A of 7 is 8, and A of 8 is 9. It would be an integer, and it's 9. This song is really nice. What song is this? Can't see all of it. Echoes. Odessa? Odessa? I like it. Thanks for seeing me and stopping by, especially since you're like, you know, taking down your total Twitch consumption. Makes me feel as special as my own. Okay. First, A of 1 is going to give us 2, and what does C of 2 give us? So we need to know B of 1 as well. So first we need to know, we gotta take some little notes. So we know that A of 1 is 2. What is B of 1? It's going to return 2, but 2.0 as a float. Okay, what's C going to do with those? The animated overlays, you like them? Streamlabs OBS is so simple. It really is. Like, I could even do it. You all see how much I struggle with this. So, yeah. And then they have a whole bunch of just to choose from their library, and then you just set it up, and that's it. Really easy. Return x plus y, so we are going to get to 4.0 is going to be our return. 4.0. Why? Because an imagine this float is a float. You're gonna get a float, and it's gonna be floating around. All right, what's this one? Throw that note one away. So wasteful. So wasteful. Yeah, that's true. That's true. But like, it's easy to have minimalism when like, you know, you only have like 1, 2, or 3 viewers. Nobody's really following, so you don't get like all the interruptions and stuff. Yeah, but I mean, we all know I like have you seen my keyboard? It's got LED lights that like flash in a rainbow across them. And my last mouse was hot pink, covered in rhinestones. It was uncomfortable as shit, but I loved it. So like, I don't know, trashy and fantastic. Trash-tastic. All right, so we have D of Apple. And what languages do you know? I know you have to know some coding languages. Do you know Python? Do you do JavaScript? Can be of any type, return x greater than or equal to y. It's going to return false. We're going to get a Boolean, and it's going to return false. Because there's no way Apple is bigger than 11.1. How do you even... Or maybe it returns an error, right? It won't return false. It can't be evaluated, right? What happens if it can't be evaluated? None-type error. It's not a function, but it would cause an error. So none-type error. PHP, but it's a big programming language. Good job to get by. So this is error. Okay. Now we do another one. So A of 3 is going to be 4. B of 4 is going to be 5.0. Oops. I hope so, but I feel like I set a really maybe over ambitious hurdle for myself by saying like the first thing I'm going to do with Python is make this. This is why I'm learning Python, is so I can make this. And not realizing the amount of like learning that takes to get from like I know nothing all the way up to like I've actually made something that's moderately complex. So I'm saying it's a journey. I'm on it, right? Try to like take the pressure off, be like I took one step forward today, or I learned something today. We're still on the path that will lead to the end goal. Let's see. 3, 4. What's C of 3 for? Let's see. I think we add them together, right? And it's 3, 4 would be integer, so that would be 7. Integer. And what does E do? Let's see. Could be any type, X, Y, Z. So we want, this is X and Y and Z. Or Z, right? Yes, but sometimes that can lead to like I agree, it's better to like, you know, shoot for the stars and land at the moon, right? At the same time, sometimes the frustration of like not being able to get there can get to me for sure. So sometimes I have to like set the bar a little bit lower for myself on a daily basis so I can make it through. like, I guess an overall high goal, but then daily, like, be reasonable, small steps, get there eventually. I feel like, I don't know, every once in a while, the more I learn about Python, I feel like the more that this project has become like this gigantic mountain. Like at first I thought it was going to be something kind of like, oh, no problem, this should be easy. I can think about it and think of it, I can do it, right? So we need to know if x is greater than or equal to y, and right? Writing's like the easiest thing in the world. I can totally write a book then, right? Yes, that's kind of what I've done with this. I think, I mean, to be honest, that's probably like a uniquely American thing where it's just like, I can do anything, god damn it. Not even thinking like, because I'm American, but that's just kind of like the culture that you're brought up in, is that like, you can do anything. You're in America. Oh my goodness. So x is 4 and y is 5.0. This one will equal false. X is 4 less than or equal to 7. That's true. But since they're and, false and true is true. So this one will return a Boolean true. Oops. Okay, and F, it doesn't even have anything. This is going to return an error because it's not even correct syntax. Okay, let's try it. Let's see. Did we get it right? Channel my inner America. No! Look at all these I got wrong. Damn! Okay. These 3 here at the bottom. Uh-oh. Hold on 1 second. Thank you. Only the second time today. This is the first time I got caught. I'll say that. I'll say that. Bullshit. 30% less on the music. Okay, let's see here. I guess I can do this. How's that? Permanently on. Yeah, but you know, I don't like to do that because we have to keep going calls and stuff. Call us and things. That's good. Okay. Right. Next. value of the expression being evaluated, evaluated expression results in error, select untype right error, the results of function, select function right function. It's always trying to do this properly and before trying to change it. Yes. Top Gun 2 is in the works? No. No. Is Tom Cruise still going to be in it? That would be nuts, because he's still making those movies. It's crazy.
Remember Cocoon?
Right?
You remember Cocoon? You remember Wilfred Brimley in Cocoon?
Yeah, yeah.
You know how old he was in that movie? No, it doesn't matter.
Younger than Tom Cruise is now?
Younger than Tom Cruise is right now.
That's crazy. Val Kilmer's not going to cut it, I think. Maybe not. Maybe not. I also heard there's a Shia LaBeouf movie coming out where Shia LaBeouf, it's like the story of Shia LaBeouf, and he plays his father and other people play him as himself and as a kid. Kilmer. LaBeouf is too weird. I think it's I kind of feel like, was he the person to pitch this movie? And if so, how is the script so enticing that people are like, yes, we have to make this movie. You're right. It's going to make so much money. Like, I don't get it. I don't understand that. I don't understand it. But I feel like he should have, with how ridiculous that is, he should have just gone full Eddie Murphy and been like every single character. Done the Nutty Professor. Everyone gets paid. Yep. Why does anybody do anything? Get paid.
No one goes full Eddie Murphy.
No one goes full Eddie Murphy. I know, but it just seems so ridiculous. That seems like, you know, if you're going to be ridiculous, be completely ridiculous. Maybe that's like an American thing too, which is how we get Trump. Like, right? If you're going to lie, really lie. Lie about everything, up and down, left and right. Yes is no. No means yes. We've always been at war with East Asia, Eurasia, whatever you want to call it. Anything. Make up a totally new country and say we're at war with it. Open up tariffs with Puerto Rico. Even Puerto Rico is American. Sure. Do whatever you like. Yes. Yes. It is like, I mean, I'm laughing, but at the same time, like, that shit is terrifying. I'm not lying. I have a go bag, and it's got, like, passports, cash, like, all the titles, marriage licenses, birth certificates, like, that shit's ready to go. I'm not digging around for that. That's the, like, whoop. Right?
Walking up to Canada and Carolyn like The Walking Dead.
That's hilarious. We have the best nukes. Yes, all the nukes. It only takes like one. Yes, I know. You guys have had like a horrible relationship with them forever. So you must be feeling fantastic about how we're like, hey, we're helping them become a superpower again, because I guess when America was great again was the 80s during the Cold War. Like, I don't even know. Right? The closer you are, the more safe you are. I don't know about that. Maybe that's why some people still like continue to be hired and work there in the administration, because they figure they'll be safe there. I don't know. He's passing out pardons to everybody. He's trying to tell them they'll be safe. Okay, A is pulse 2 and 3. Okay. No, I haven't.
Oh, here you go. Here's a close-up picture.
Close up of what?
She like his father. That's the way
That's crazy. And also, like, does his father know about this? It's crazy.
Oh yeah. Like he had reportedly he had a crazy relationship with his father. The guy used to perform as a clown, became a heroin addict. Like
That's crazy.
like
Kind of want to see it, but you don't know.
and also an alcoholic. Sure.
Everything all rolled into one.
Yeah, a total clusterfuck.
I'll probably go see it as like, oh god, these kids are driving me crazy. What are we gonna do? Let's go see Solo. It's like something to do. Or like it's so hot, you can't go outside unless there's air conditioning. That's when you hit the movie theater. Better go to the movies than drug them, I guess. I suppose so. Okay. So A says, if X, so it's false, which means it's not going to return Y. It's going to return Z. And Z is 3, it is an integer, and it is what will be returned. B, it's going to be Boolean, right? Right? I've got my Kindle and lots of batteries. I ran out of space for books on shelves years ago. Way too long ago. It's almost time for another Colleen where I'm kind of like, the only books I keep like physical copies of are favorites, like complete favorites, things that I've read like a couple of times. So. Things that are important, you know, important reads. Yes, that's true. That's true. I forget. Sorry. I'm stupid American right now. Everybody speaks English, right? Yeah, that's true. I forget so much of the internet is in English, just like a lot of businesses in English. But I think that will, yeah, we'll see. I don't even know another language well enough to like read anything in it and get like the same thing out of it. Return, okay, so first it's 3, 2, and we're gonna return A. Oh, I see what they're doing. That's interesting. Okay, so now we need to look at A if it's true. Ah. Well, you know, you can read any PDF on a Kindle. So that works. Okay. Q, R. So if 3 is greater than 2, true. So A is true. Q was 3 and 2. And now we run it through A, which is if true, return Y. So it should return 3. And that's it. So it's not this one. Wait. No, what did I do? It doesn't return Boolean. It returns integer and it returns 3. Right? Because it returns Y and Y is 3. Y is Q. All right, 3. Okay. All right, we did that one. Focus, focus. I know. Okay, yes. It's true. I have a little bit of time left. Like, but I have to tell you, this, when we started, it was like, oh yeah, this section here is section 4. It will take you 1 hour and 8 minutes. I've already been at it for 2 hours and 20 minutes, and I was not entirely distracted. I did a lot of stuff and watched a lot of things, but I also took like a few pages of notes. Where did I start today taking notes? 1, 2, 3, 4, 5, 6 pages of handwritten notes so far, and we're like not very far into it. This is way more in depth, I think, than the other one, but I feel like this one is even doable because I did the other one first, which was very basic and a lot of hand holding, so it's okay. So function of that 3 greater than 2 is true. So it's A true, A, B, and then it's true, so we return Y, and Y is A, so it's going to, is that a function? Is it, what's it going to return? Function A? I don't know, we'll try that one. And then you didn't tell me what kind of beer you were drinking earlier with your friends. How much beer did you drink? Tell me all about the good time that you had. EAB, so that is, this can't return anything, right? Does it just return a function? Does that just return function too?
That's just my phone. Unless my brother.
Cool. One number.
No, don't answer. I don't care who it is. Nobody's calling me. I don't know nobody. I don't think this is the right answer though. Let's see. BAB. A is bigger than B, which it's not. That's false. So then it would return C, which would be R, which would be E. Maybe. Let's see what happens. Nope. And it's okay. This one is a function, but doesn't return A. We're just going to say function, I guess. And then, is that right? Yes. And this doesn't return a function. We're going to say it returns error. Yeah! I did it! I like this song too. Carbon-based life forms. That's who does this song. Okay. Okay, A is 10. A is 3, F1. Return X plus A. It's definitely an integer. What's it going to be? Is it going to be 11 or is it going to be 4? Is the global 10 or is the global 3? I think it's going to be 4 because this global isn't run, it's just the function here that's run. And this A is going to reference outside. Which outside? This one, I'm guessing, because you're saying A equals 3. So we start with A equals 10, and then we say, no, never mind, A equals 3. and now do that function. So it's 4. It's 4. X equals 12. Define g of x to be x equal to x plus 1. We define h of y to be returning x plus y. And then we return h of 6 gx. H of 6 is okay. All right, let's work through this one. So g of x, x is 12. So, and then so on top of that, it's not 12, it's 13. It's 13. Then we define that to be 12 plus that,
Yes.
return h6.
Hi. Yeah.
I don't think this is exactly, I need to do it as like
All right.
different scopes. So this is g of x. X is 13. Right. And then we do h of y. And there, we return x plus y, which is 12 plus y, and then h of 6 is going to be 18.
So show me what's wrong.
Integer
On non-real life, it's good, right? Okay.
18. Let's try that. Damn, it's not 18 though. What is it? When it goes back, x isn't defined. Is that correct? No. When it goes back, x is 12. No.
Yeah.
X is 13. So it's 19.
Okay.
Yes.
All right.
So close.
Let's see what we can do.
Next. All right.
So,
See how far we can get through this one. Change pen colors again. I feel like this color will be nice.
because I can see it. For me,
Now that we've introduced the idea of a definition function in particular as a way of doing encapsulation of information, we can start exploring some of the variations to them. And I want to show you one place in Python that's actually can be very handy. And that is that I can have a function definition that I can change in terms of how I want to think about invoking it. So let's start with a simple function here. This is a very simple function that says if the last argument is true, then I'm going to print the last name, comma, first name. Otherwise, I'm going to print the first name, comma, followed by the last name. And I'm going to expect those to be strings. And I've got a simple little implementation of over here. I'm going to import it into my Python shell so I can use it.
Sorry.
But at this stage, you can hopefully look at this function and realize, given some value for reverse, I'm going to test that. If it's true, I'm going to do this, which is just a print. I'm not going to return anything. If it's false, I'm going to do that. Okay? Now, here's one of the nice variations on it. First of all, that first call does sort of what I'd expect. And in fact, if I go to my Python and type it in, I can say if I do print name, and I'll do myself, of Eric Crimson,
all right.
and I give false
Next thing.
as the value for reverse, it prints it out in the order I expected. I could do, by the way, the same thing. I could say print name just to show you it does the right thing of Eric and Grimson. Notice the commas, by the way, to separate the parameters. And I give it true. It would help if I can type, so I'll do it one more time with Eric Grimson and true. Now it prints it out in the other order. But here are some of the variations. I could say explicitly, give the binding to the parameter name reverse the value false. So doing it in the same place, but I can actually specify it. I could similarly for any of the parameters in the invocation literally say the parameter followed by an equal sign and the value that I want. And all three of these are going to print out exactly the same thing, and in fact so will the last one. But notice here I've reversed the order. So if I'm not going to use this kind of formalism, I have to give the parameter in the place it expects. But in this case, I reversed it. Even though the function expects first name, then last name, I've said I'm going to have last name have the binding Grimson, first name have the binding Eric, and reverse equal to false. That's nice if I forget the order, or if I just decide I want to call them in a different way. I can do some other things here, though. I can change the definition of my function to give a default value to one of the parameters. In this case, the syntax is there's the parameter name, and I'm saying let it have initially the binding of false. And that means that if I call the function, as I do right here, without an explicit parameter passed in or value passed in for that parameter, the default holds true. In this case, I'm going to assume that reverse is false, and therefore I'm going to do this particular print statement. On the other hand, if I want to change the value of that, I need to give it an explicit value to overwrite the default value. And this is handy if I've got a parameter that normally I expect just to have a particular value, but on rare occasions I might want to change it. My invocations don't have to always pass in those values. So a nice little variation on how we pass values in to parameters of definitions of functions.
Okay. I feel like we'll probably need some of that later, but next, we'll come back and watch it again later if we need to.
We've now begun to look at functions. We're going to do more of those in a second, but it's important to take a little break here to talk about one other piece of a function, and that was the idea of a specification.
Okay. What are specifications? This isn't a job interview class shirt, though. What? That shirt that he's wearing, my shirt that I'm wearing, his shirt, your shirt. What are you talking about? The guy here, okay. But he's trying to be like, I'm cool, I'm hip, I'm relaxed, I'm with it. That's what's going on there. That's why there's no time. Loosen up. Look, he's not wearing the like coder uniform, right? Which is like t-shirt, hoodie, jeans, sneakers, right? If you're a woman, it's just like yoga pants and a t-shirt. Maybe that's just me. But I bet you if you asked the millennial developer. I'm kind of on the cusp. I'm like the oldest of the millennials, like a little bit out there further. It's just a little. Although I feel like I should lie more about my age and see how much I could get away with. Like 27. No problem. That's completely believable. Maybe. I bet if I say it confidently enough, people would believe it. There was a whole TV show that did that. What was it called? I forget. But it was this woman who was like 40 and she was trying to get back into like editing, and she felt like she was being like discriminated against because of her age. So then she started telling everybody she was like 27 or 28, and everybody was like believing it. It was crazy. It led to some hilarious situations. Specifications. All right. Focus. Only embarrassing if you get caught. Not really. I'd just be like, haha, JK. Do you watch anime? Because I found an anime that I like am obsessed
Do
with.
you mind if I tinker with this for the next 20 minutes or something? Alright, I'll call you right back to this.
But really, I would not get caught because who's going to call a woman out on her age? Like, if I say I'm 27, nobody's going to be like, really? You look older than that. Like, nobody's going to do that. Hayward. Hey. Assumptions. I feel like if it's a long time and then I get caught, then that's embarrassing for them too. Yeah, exactly. If they believe it for that long, then they should be the ones who are embarrassed. Like, haha, sucker. confirmation that I am an alpha person. Check. I don't know. This is what I'm watching. It's on Crunchyroll. Yeah. Oh, I'm Psycho 100. Oh, I spelled it wrong. I've never even heard of that one. Kabanari Iron Fortress. Where can I stream it? Oh, man.
I heard about that. It has like an attack. I heard it has like an Attack on Titan vibe.
And Berserk and Cowboy Bebop are all-time favorites, yes. I remember watching, like, the back when with Netflix you would still get, like, videos delivered. I did the whole Samurai Champloo series when I was pregnant with my first child. Attack on Titan, the trains, it's genius. Kabanari Iron Fortress, Attack on Titan, the trains. I'm gonna have to check that out. Cowboy Bebop is awesome. Streams. Jeez. I'm writing it down right now. Just avoid the new one. Okay. Old. One of the first animes I ever saw was Star Blazer. Shit was on TV when cartoons were only on Saturdays. Saturday mornings. System with assumptions. Okay.
This is something we're going to use to be able to decide how we want to use a function. And think of a specification, therefore, as a contract. We don't enforce it necessarily, but it's a contract between the implementer of the function and the people who are going to use it. That specification ideally will say, here are the assumptions. Here's what the implementer of this function assumed was going to be true, especially about the values of parameters. If you like, it's the conditions that a client needs to guarantee are true before they use it. And then if those assumptions are in fact met, the second part of the specification are the guarantees. It says, here's what the function will do, provided it's been called in a manner consistent with the assumptions. The way we do it in Python is to use this idea of a docstring. And there's my earlier definition of isEven. It has a condition on the input. It says, if you give me an integer, which I'm calling I, in particular a positive integer, then here's what I guarantee, that it will return true if I is even, otherwise it's going to return false. Now, you're not required to put in a docstring or a spec, but good programmers always do, in part because somebody else might use this and you want to tell them how you expect it to be used, or because a year from now, 2 years from now, you may come back to this function and you'd like to know, what was I thinking when I built it? So I encourage you to build your own docstrings, even though it takes a little more time, because it helps you understand what's expected of a piece of code and where can I use it.
Okay, what's next? Ooh, more problems. Yay! Maybe we get through these problems and then I call it for the weekend. So we're getting close to time. comma 5. R3, return 4, return, so it's going to return 4, comma 10. It's going to be the same thing because even though it's 0 here, it's going to be assigned as 5 there. 2. So it's here. Is this one then 2 and 0? So we return 2 and 3, comma 2. Oh, wait. Oh, now I get it. Okay, hold on. Hold on. Wait a minute. Okay. Bar is this one here, the name of this one it's calling. So it's going to throw it through again. Right? So the first one is 4. And then when we put it in here as 5 times 2 bar of 10, it's going to give us 11. Yes. Now this one. Three, 0. So that's 3 and 5. And then we say bar 3 is 4, and we're going to return that one. And then we're going to say return bar of 10, which is going to be 11, correct? I think so. Or, yes, because it's still inside this one where it's been defined. I believe so. I believe so. And then this one, 2. C, comma, 0. Return C plus 0 is we return Z. And bar 3x, so this would be 3, 0, and then we return 3. Sorry, punch in my microphone. Let's see if that'll work. And then 5, it would be the same thing here where it's 0, it's Z, and then bar 3 is going to be 3. C, comma 3 again. Right? Because it doesn't matter what this is here. Because we reassign what x is. Unless is Z then become 2. And 0, 2 and 0. This would be 2, 3. I don't know. Let's see what happens. Let's submit and see what happens. Okay. So I got them all wrong. Every single one. Awesome. Let's put this in. My spider never opened. Let's close this. Let's see if I can open it again. Might be a bit heavy on my. Open! I don't think that's what I necessarily want. But let's see what happens. Oh, it's working. Right? I gotta keep it low key, you know? I find it difficult to like learn and listen and do all that stuff with like music that has words. So I try to get like something. Why is this taking so long? There we go. About time. It's almost 2 p.m. here. Or 1,400 hours. There we go. So I'm going to start a new one. And we're gonna take this stuff here and put it in this and run it and see what we get. And y is 5, right? And 3, is it x plus 1? Or is the x carried down? I don't know. Let's run it and see what happens. Cancel. Oh, I have to save it before. Maybe. Sure. All right, run it. So it was the second number. It doesn't return the 4 because why? We're not defining a bar x until it comes all the way through and then goes back again. So it's the 5. Or 10 is 11. Okay, let's see if that works. From 0. Wait, no, we're just returning this, which is c plus x, so that's 3. Okay, getting closer, getting closer. What do these return instead? So we have 3, 0, and we put it in there, and we say instead 3, 5. And then we say return bar 10, so it should be 11 again, but it's not. Is it because this is within this function? This is not within this function. And we say, so x would be 10 here then. Y times 2 should be 11 again, but it's not. Let's see what the, oh, I don't get like outputs or anything here. Let's try this. I know what I'll do. I don't need to do any of that. We're just going to say 3, 0. 1. Why 1? Why is this 1? Zero plus 1. So this out here takes precedent over this. And then that's 0, bar of 0 is 1. Okay. So foo 2 is 2. We define within that bar to be z and 0, z, 0, return z plus 0, return bar 3, x. So it's not 3. Is it 5? Okay, so the x is the same throughout, and we are saying put 2 in here for x. So in here it's 0, but out here, when we come out here, x is 2. And so it's 3 plus 5. Okay, got it. "20 minutes. Oh, good Lord. This might be the last one that we complete. If we complete it, this will be the last one. Everything in Python is an object. Objects are special because we can associate special functions referred to as object methods within the object. This problem will work with string objects and other built-in methods." Okay. It's good convention for objects is to use the dot notation so that if S is a string, evaluating S upper will return the actual function, and evaluating S upper in parentheses will cause the function itself to be evaluated. In this case, returns from strings, since strings are immutable. With every character now uppercase. Okay. So let's see, it's still capitalized. Okay. This problem specify its type and value generates an error in that type. Return arrays, yes. I was only just starting to get into those in here. For this one, definitely not yet. I don't think so. We haven't even gotten to classes in this one yet. Okay, string 1 is an exterminate. String 2 is number 1, the large. Okay. Assume the expressions are evaluated in the order shown. That is, each problem part is evaluated directly after the previous problem parts. Those are the best. So if that's sarcastic or not. Alright. String 1 upper. String. It's upper, which means they'll all be uppercase. Oh, no, it won't because it doesn't have the parentheses after it. So it's actually going to be a none type. Oh, to return the function. How do I write that? Do I just write function? Yes. Okay. A lot of arrays in e-commerce. Okay. I've been sitting for a while. It's not a favorite. Okay, this is going to be a string, and it's going to be that. Wait, yes, because it's saying it does it in a new. Yes, cause the function itself to be evaluated, returning a new string since strings are immutable, which means that if we ask for string 1 again, it's still going to give us lowercase. Yes. String 1 is upper, Boolean, false. String 1 is lower, Boolean, true. String 1 equals string 2, capitalize. String 2. String, and string 2 was what? And capitalize would be the first letter there. Number 1. I know. I do yoga every day and it's still not enough. Not every day, okay, like on average 5 out of 7 days a week, but still not enough. Yeah, it's too late. I feel it like I can hear like popping in my neck and stuff. It's too long. And it's been like what, 3 hours? 3 hours is when I start to get like, that's okay. We're gonna get through this one. So this would be number 1. A large. Space there. Doesn't capitalize. Wonder if it capitalizes each word or just the very first one. I don't know. Swap case, string 2, swap case, string 2. Is that right? I don't know. Index of P is going to return an integer because string 1 index of P is Ooh, 1, 0, 0, 3. X, E, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is it going to put them all out? I don't know if it's going to do all of them or just one. I don't know. 0, 3, 10. String 2 index N. 0, 1, 2, 3, 4, 5, 6, 7, 8. 0 and 8. Find N. I don't know what find does. String 2 index. That's gonna be like none type error or none. So it's not going to, there is no exclamation point in the second string. Maybe this is false. I'm going to call this true. I don't even know if that's it, but that's what we're going to do. Also, does this sound okay? Because I literally have an air conditioner like arm's distance away from my head. I tried to like do some more noise canceling. Turn that noise canceling all the way up. But I don't know like what it's doing to the rest of the sound. Count E. Measure. Count E is going to be for string 1. It's 4, right? 1, 2. No, it's only 3. 3. Replace E with stars. We're gonna get but let's see, what else did we do with string 1 here? We counted the E's. Did we change it any other way? Last time we saw it was all lowercase, I think. But it's not Saturday. Still spring. It's like, it's not really hot, but it's so humid today. We had to turn on the air conditioner. It's 87% humidity. So even though it's like 22C or 21C, it's just too, it feels hotter than it is because your body can't get rid of any excess heat. String 2 replace 1, 7. don't know if it's going to do anything because we don't have lowercase ones anymore. No, yes we do. It's going to give us a string, and it's going to say number 7 March. There we go. All right, let's see. That's only because you're white. Doesn't do so good on people of color spaces. Okay, so this one doesn't work. And these ones don't work. Okay, I got some of them, but not all of them. Okay, so string is upper. String 1 is upper. Is true. It is an integer. Okay, let's say 0. It's going to return the first one. Try that. String 2, find n. We're not going to find a lowercase n, are we? False. Oh, it's not Boolean. Is it going to give us where n is? And we're going to say 0 because it's an index 0 and index the other one. Is it going to give us all the indexes? I don't know. None type is true. Oh. Here we go. So find is not Boolean. It's going to be, I don't know. Is it going to be a string and just give us a string of numbers? I don't know. Find exclamation point in string 2 is going to be actually an error, right? Non-type error. Maybe? Yeah, that's why I'm sure you've probably seen it, but like in futuristic things, where there's a lot of like facial recognition stuff, people who like try to fly under the radar put like tattoos on their face and stuff to like break up the facial recognition. Nope, okay. So it is an integer, but it's not 0. Index of n. How is it going to print it out? It's Boolean, but it's not true and it's not false. I thought those were the only two options. True and false. True or false. Okay. Let's look for answers. Oh, it was a capital number. So this is string, capital N number. So close. That one's right. That one's right. It's an integer. Why is it -1? I have no idea why. Let's see if we can figure it out in the comments below. 8. Let's see. String 2, index 8, find index n and find n are both 8. Let's see which. Why? I have no idea. String 2 is number 1, the large, right? But why is this 8? Oh, because I start counting from 0. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So why doesn't it count this one? Because it's capitalized. That's why. Okay, I think I got all this. I still don't know. This one's false. I thought I did have false there. And then it was like, nah. All right. Yeah! Yeah, I want to know this one. Why does it return -1? There isn't an exclamation in string 2. Okay. Ah, so it will return -1 on failure. That's why. Okay. I figured someone would ask that question. We have another one? Yes. Oh, but I don't think we're gonna have time. It says 2 minutes. Okay, let's see. Write a Python function 4th power that takes one number and returns the value raised to the 4th. You should use square procedure that you defined in an earlier exercise. You don't need to redefine square in this box. When you call square, the grader will use our definition. Return square star square. Wonder if that works. Incorrect. What's the output? Square x to the square x. Let's try that. No. It's still giving me the same pissed off thing. Doesn't want me to use those? Fine. We'll do the square of the square. Yes! I knew it! My math skills are strong. Next. 3 minutes. Maybe we can do this one too. Oh my god. I'm like excited I'll get all the way through to the endpoint I picked today. Let's see. Write a Python function odd that takes one number and returns true when the number is odd and false otherwise. You should use modulo, not if. The function takes in one number and returns a boolean. X modulo much productive. Low in this Friday. Right up. X modulo 2 equals 0. quite sure. Okay, or the other side of the coin, return Boolean x modulo 2. So if we say bool, right, it's B-O-O-L, yeah. That will turn it into a Boolean response, and so if it's 0, it's false, and if it's 1, it's true. Yes. Right? Yeah. That's why. Okay. I'm done. Cheated a little bit on that one, but that's okay. Correct. No, I didn't cheat. I used the resources available to me to find the solution. Okay, so we'll start next week with recursive function scope example. Thank you for stopping by, Gavlogs, and I hope you have a great weekend. It's already like Saturday for you there, right? And that's it for me. So see you all next time.